All right, today's lesson is on nonlinear functions. So, the essential question for today is, how do nonlinear functions differ from linear functions? So, we've learned about how to represent functions, how to see and recognize if something is a function, and then yesterday we learned about linear functions, which are ones that have a constant rate of change and create straight lines. Today we are going to learn about nonlinear functions, and these are functions that do not have a constant rate of change, and they do not create straight lines. So we have 6 graphs here. You are going to label them as nonlinear and linear. So remember, linear functions create straight lines. There are no breaks in the lines. There are no curves in the lines. They are exactly straight. So when I'm looking at these, I am deciding if it's linear or nonlinear. So this first one, curves. This is a nonlinear line. The fact that it curves, it is not straight, does not make it a linear function. The second one, it curves again. So what do you think it is? If you said nonlinear, you are correct. The third one, linear or nonlinear. It is a straight line. It does not curve, it does not break. This is linear. The fourth one, again, it is nonlinear because of the curved piece of it. The fifth one is a linear function. It creates a straight line, which means it has a constant rate of change. And this last one, you may be thinking it's linear because look, it's straight and straight, but the fact that it breaks and it goes up and then down does make it a linear function. You have to have it where it is continuously going straight, continuously going straight. The fact that it goes up, breaks, and goes down, that results in it being a nonlinear function. So now looking at tables, decide which one represents a nonlinear function or which ones. So just like we did yesterday, we are going to looking at the constant rate of change. If my input and output go up or down by the same rate, it is considered linear. If they don't, it is considered nonlinear. So as we are working with our input here, each one of the first ones is going up by 1. My output, I go down 8, because I'm subtracting to go from negative 16 to negative 24. I decrease by 8. Again, down 8 and down 8. Well, the fact that this is consistent, this means that this is actually a linear function. So it is not one that we are looking for because we're looking for nonlinear. All right, my inputs on this next one. Each of my inputs is going up by 1.
Mommy,
what?
It's going to die. It's going to die. Look.
It's okay, then go with this one here. Here, there you go.
Okay. This can have function.
Okay, I'll take that, thank you. All right, so now the second one.
Hi, Siri.
Edie, shh. This first one, sorry. All right, on the second one, your inputs are going up by 1. Now your output, 1.5 to 2.5 is increasing by 1. There you go. Is increasing by 1. From 2.5 to 5.5, it is increasing by 3. Well, right away, are those the same values? They are not. We want to have them constant. So this is actually a nonlinear table. Excuse me. And then on letter C, each of my inputs are also going up by 1. So those are constant. The fact that my inputs are constant, my outputs need to also be. From 1 to 3, it's up 2. 3 to 6, it's up 3. 6 to 10, it's up 4. And then it's up 5. Are all of my outputs increasing by the same amount? No. So letter C is also a nonlinear function. So if they are constant, it's linear. If they're non, it's nonlinear. All right, so this next one, nonlinear from a situation. So we need to change our table up a little bit. So suppose there are 20 rabbits on an island. So we start at 20 rabbits. And the population triples every 6 months. So that means that we are multiplying by 3. We need to make a table of values to show how many rabbits there would be after 2 years. So this is what I need us to change. Instead of it being 0, 1, 2, I want us to change this to 6, 12, 18. So what I'm doing is I'm counting up by 6s to make it be where it triples every 6 months. So we're going to make these by 6s. 38. 38? No, I did something wrong here. This is what I did wrong. This should be 24, then 30, and then 36. So this is telling me at 3 years, we're at 36. 24 is going to be at our 2-year mark. So if I look through these, at 0, we started with 20 rabbits. So that's our starting piece. Now if they triple, we are going to multiply every time by 3. So 20, I am going to multiply by 3, and I get 60. So after 6 months, we're at 60 rabbits. When I multiply that by 3, we're at 180. When I multiply that by 3, 180 by 3, I get 540. When I multiply that by 3, I get 1,620. When I multiply that by 3, I get 4,860. And then when I multiply that by 3, I get 14,580. So, how many will there be after 2 years? 1,620. Is this a nonlinear function? Yes, because it does not go up by a constant rate. Not a constant rate. And then we want to know when it will be about 1,000,000. So if I keep multiplying up, so at 44 months, I'll be at 43,740. And then at 4 years, I'll be at 131,220. And then at 4.5, so right around 5 years. Because if I keep multiplying up, it's right before 5 years, I get to be at a little over 1,000,000. So when it says it's going to triple every single time you multiply it by 3. All right, this last one, is this linear or nonlinear? Well, I go up by 2, 2, 2, 2. So this is that. Now this one, I go up. I mean, I don't even have to show you the numbers, and I can tell you what it is. Up, and then look at this. Down, down. Well, can a linear relationship go up and then down? This is showing me that I would be going up, 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 down, down, down. Is that a linear relationship? No, non-linear. And you can explain it of it increases and then it decreases. And using this table, why can't we predict the bat population? There's no constant rate. If it was a constant rate, we'd be able to predict it. But the fact that it goes up and then down, for all we know is in 2009 it could increase, and in 2011 it could decrease. All right, that is it. We will summarize tomorrow.